How did you guys do on working through this? 38 and 39? Mm-hmm. Shall we go over it?
Yeah.
Yeah, I thought so. Okay. Thank you. Now, you can always decrease a hydroxide ion concentration by adding an acid. Does that make sense?
Yeah.
So if your compound has hydroxide in it, like let's say you had, on the previous page, we had calcium hydroxide, CaOH2, Ca2 plus 2OH minus. We can always decrease concentration of calcium, of hydroxide by adding an acid. For example, what would be a good example of an acid? HCl. Yes? Always nice. You could choose HNO3. HNO3 would also be a good choice. Now, the next one is just something that you will need to remember. Or you can play the odds and say, I probably won't need to know that. Right? It could come up or it might not. It's one of those things where every once in a while there is a question on carbonate and often there is not. But if you're going to university and you're going to take chemistry, this is a worthwhile thing to know anyway. How many of you have reacted vinegar and baking soda? What happens? What do you get?
Bubbles.
Bubbles. Bubbles. So what is happening, it's a little bit different for baking soda, but this is going to help you remember, is that you have the acid, right, which is like the vinegar, and you have the carbonate, which is like the baking soda. And the acid, which is like vinegar. And you'll notice that the CO3 2- is acting as a Bronsted-Lowry base. And it is a weak base, so it would tend to go back and forth and back and forth. But there is another step. And you remember how you said you got bubbles? What do you think those bubbles might be made of, given that you're starting with H2CO3? CO2, which is the bubbles. That's a gas. And who would our other product be? Water, H2O. Okay, so if you add an acid to a carbonate, it will react with the carbonate and make CO2 and H2O, which will cause the concentration of CO3 2- to decrease. Okay. And the other thing that you should know is that you can sometimes, not always, decrease other ions by adding something that will precipitate them. So you can decrease hydroxide by adding an acid, you can decrease carbonate by adding an acid, and you can sometimes decrease other ions by adding something that will precipitate them. So, how can we increase the solubility of MgCO3. Now, before we start on this, I would like you to define the term solubility for your neighbors. What is solubility? Solubility is the maximum of solute, and in this unit, that's going to be referring to the solid that can dissolve yes. Oh, thank you, thank you. My brain does things. Do you know what happened to me the other day? I went to get my ingredients to make dinner out of my fridge, and you know what I found in my fridge? My hairbrush. And I'm like, oh, because at lunchtime I had leftovers for lunch, and I was chatting with my son, and I was brushing my hair because I just, like I'd gotten out of the shower and whatever, my hair was all tangled. And so I'm brushing my hair and I'm going to get my lunch. And I guess I went into the fridge and got my lunch and put down my hairbrush. And then at dinner time, I'm like, why is there a hairbrush in the fridge? Anyway, that's my life. So sometimes I write solid, twice when I mean solute. Oh dear. I will never know if I get dementia because I cannot remember things. I get everything wrong. I call things by the wrong name. It's okay. All right, so the maximum amount of solid that can dissolve in a given amount of solution. So basically, we are looking at the amount of solid that will dissolve. So if we're wanting to increase the solubility, if we want to increase the amount of solid that will dissolve, what could we do to this equilibrium? We could add H. I would choose a strong acid instead of a weak acid. So HCl. HCl is a good choice. HNO3 is a good choice. So we're going to add HCl or HNO3. And what reaction takes place if we add HCl or HNO3? We get H plus, what does it react with? CO3, 2 minus. I would like you guys to predict the products of that reaction and balance it. Sorry. I'm like halfway through. Yeah. Hopefully by tomorrow. So we have HCO3. What is our product?
H2O and CO2.
H2O and CO2. I'm actually going to go through the intermediate compound in the middle, H2CO3, which means we need 2 of those, and then that will form CO2 plus H2O. Is good? Okay. So what does that do that causes this equilibrium to shift? Therefore, the concentration of CO3 will decrease. And if CO3 2 minus decreases, tell your partner which direction the equilibrium will shift. The equilibrium will shift. Right. Because we want to replace the CO3 that was lost. And if we shift right, do we have more solid dissolved or less solid dissolved?
More solid dissolved.
Is it more or is it less? Everybody. More. Because if we're going to the right, we're dissolving more, okay? More solid dissolves. Therefore, what has happened to the solubility?
Solubility has increased.
Now, when we have a question like this next one, in which will you be able to dissolve the greatest mass of CaOH2? What we're doing is we can kind of compare each of these solutions to water. Water is sort of the normal solubility, okay? But we have a beaker containing Ca, NO3, 2. We have a beaker containing NaCl, another one containing HCl, and another one containing NaOH. And into that, we are going to dump some CaOH2 solid. Which of those will, in which of those will you be able to dissolve the greatest mass of CaOH2? So what you're going to do is you're going to look at each of those ions and say, what is it going to do to the solubility? And I'll start you out by saying this one, you're going to look and you're going to say, I've got extra Ca and I have extra NO3 minus. And you're going to look at this and say, what does that do to my equilibrium over here? And how does that affect how much mass can dissolve? You're going to try those. I'm going to come around and see how you're doing. Okay? But before that, I'm going to get myself some water because I'm really thirsty. But I'll be right back, so get started. Yeah. Here. So we've already done calcium ions present. We're trying to develop another substance. Okay. Yeah. Okay. Okay. Yeah. Ramble away. Work it out. Yeah. Yeah. No. Yeah, the CL won't react. The H won't react. So the concentration of OH usually this is almost the same sort of it's so neat. What is that? It's like so Okay, so I feel like most of you have gotten it, or at least are getting there. So if we have this calcium here, calcium ion concentration has gone up, so we shift to the left, so there's less solid dissolved. So will we be able to dissolve the greatest mass? No. If we have Na, what do Na and Cl do? They do nothing. If you look at your solubility table, sodium is soluble with everything, and chloride only precipitates with silver, lead, and copper 1. So this would be the same solubility as in regular water. So this one has a lower solubility. Same solubility as regular water. Now, how about our H+? Yes, we end up with H+ reacts with OH. And what does that do to our OH concentration? It decreases it. Yes. Which shifts the equilibrium to the right, which causes an increase in solubility. And how about NaOH?
It brings up the OH concentration, it will shift left again.
Okay, and so we have a decreased solubility. Now, the next question is actually way harder than I meant it to be. We are going to go through it, but I would not give you anything like this in a multiple choice question because it actually involves a fair chunk of math. Technically, 3.2 is not our math section, so this is a preview math. Are we good with that? So if you don't understand the math today, don't beat yourself up. We're going to go over it again later, all right? But we can eliminate 2 choices because the degree to which an ion affects the solubility depends upon its concentration. The more concentration, the more it affects the solubility. Okay, so the only thing we can actually do in this question is we can say which of A and D would the solution be the least soluble? So if we're just comparing A with D, CaF2 is less soluble in which solution? D than in A. Okay, we can also compare B and C. CaF2 is less soluble in B than in A. Are we okay with that? Do we want an explanation as to why, or do we just kind of get it? Like the more you have of one of the ions, the more it's going to shift it to the left and the less soluble it will be. Does that make sense?
Yeah.
Okay, cool. Now, you'll realize why I screwed up here is the fact that CaF2 is not 1 to 1, it is 1 to 2. So, yes. Oh, B then in C. Thank you. Okay, sorry about that. We were comparing B and C. So now we are down to, now we can say, okay, if I was going to answer this overall question, I can say that it is not C and it is not A, okay? Because they are, the substance would be more soluble than in B and D. Now, if I actually want to compare B with D, this is tricky, and we actually need to do some math. Okay? So let's start with the NaF. In 0.01 molar NaF, the concentration of fluoride is equal to what? This is not a hard question. 0.01 molar. Now, what we're trying to do is we're trying to add calcium fluoride to that solution that already has F in it. CaF2, Ca2 plus 2F minus. The amount of F minus that dissolves from the CaF2 is going to be insignificant compared to 0.01 molar. Remember, this is a low solubility compound. Are you with me? Okay. So what we can do is we can write a KSP expression for CaF2, which would be concentration of calcium times concentration of fluoride squared. Yes? Okay. Now, if I wanted to solve for the concentration of calcium is equal to KSP over concentration of fluoride squared. Yes?
Yes.
Now, I looked up the KSP for CaF2. The KSP is, it's actually 3.9 times 10 to the minus 11, but I rounded it to 4.0 times 10 to the minus 11 to make the math easier. Okay? So we can plug in our KSP value, 4.0 times 10 to the negative 11. And our fluoride ion concentration, remember, 0.01 molar because the amount that comes out of the calcium fluoride is too small to worry about. And that's from the NaF. Yes? And I can't forget to square it. Are you with me? Okay. We do the math on that. And we get 4.0 times 10 to the minus 7 molar. And that is equal to our calcium concentration. Yes? And now we're going to have to hop down here. CaF2 in equilibrium with Ca2 plus 2F minus. Now our calcium ion concentration is 4.0 times 10 to the negative 7 molar. Yes? And all of that came from calcium fluoride. There's no other source of calcium ions, right? Fluoride, there was a different source of fluoride ions. We had sodium fluoride, which gave us lots of fluoride. So what would the concentration of the calcium fluoride be? Remember, this is a 1-to-1 ratio. What is the concentration of calcium fluoride? 4.0 times 10 to the negative 7 molar. And we could also, we don't need to do it for this question, but we could write the fluoride concentration. What would the fluoride concentration be? 8.0 times 10 to the minus 7 molar. Is that indeed insignificant compared with 0.1 molar, 0.01 molar? That number is much, much less than 0.01 molar. So we were correct. It was insignificant. What is solubility again? Okay, do we have that number here? How much calcium fluoride could dissolve? This is the maximum concentration of calcium fluoride that can dissolve in 0.01 molar NaF. So this is the solubility of calcium fluoride in 0.01 molar NaF. How are we feeling about that? Given that you don't need to actually solve these calculations yet on your own, but are we generally getting the idea?
Yeah.
Okay. Shall we do the same thing with our calcium nitrate solution?
Yes.
Okay. So that's okay. Look, all this room over here. Oh, and if you don't have enough room, grab yourself another piece of paper. Okay. Now we're going to look at 0.1 molar calcium nitrate. All right. And we know that KSP is equal to the concentration of calcium times the concentration of fluoride squared. So if we want the concentration of fluoride squared, that's going to be equal to the KSP divided by the concentration of Ca2 plus. Do you remember the concentration, the KSP value? 4.0 times 10 to the negative 11. And what value are we going to use for calcium concentration? 0.10 molar, because remember, how much calcium are we going to get from calcium fluoride dissociating? Are we going to get a lot or a little? A little. Remember, calcium fluoride is low solubility. Yes. So how much do we get of the calcium from here? Not very much. Certainly a lot less than we get from the calcium nitrate. So we can ignore whatever we're getting from the calcium fluoride, and we'll only use the amount from the calcium nitrate. Okay, so that's going to be divided by 0.1, and that is from CaNO3 2. So fluoride squared is going to be 4.0 times 10 to the minus 10. So concentration of fluoride is going to be the root of 4.0 times 10 to the minus 10, which is 2.0 times 10 to the minus 5 molar. So far, so good. And if it's not, it's okay, because we don't have to do the calculations until later. Okay, just go with it though, all right? Now remember, we have CaF2 in equilibrium with Ca2 plus 2F minus. And we now know that the concentration of fluoride is 2 times 10 to the minus 5 molar. That's how much can dissolve if we already have calcium ions in solution. Remember, calcium is making it less soluble, right? So we have 2.0 times 10 to the minus 5 molar. That means the concentration of calcium will be 1.0 times 10 to the minus 5 molar. And the concentration of calcium fluoride will be 1.0 times 10 to the minus 5 molar. 1.0 times 10 to the minus 5 molar. All done? Yep. Thank you. So what is solubility again? So this is the maximum concentration of CaF2 that can dissolve in 0.1 molar CaNO3 2. Therefore, this is the solubility of CaF2 in 0.1 molar CaNO3 2. Now, we have two numbers here. This is the solubility of CaF2 in 0.1 molar calcium nitrate. And over here, this is the solubility of CaF2 in 0.01 molar NaF. So we can dissolve less calcium fluoride in that sodium fluoride than we can in the 0.1 molar calcium nitrate. So the answer key is wrong. Yes. Did I use the wrong number? 0.0. Yes, we got rid of this one because it would be more soluble in that one than the other. So like I said, if you're feeling, So the answer, take a look at these two numbers. So we have NaF and CaNO3. Which one is the smaller number? The NaF. So this is the lowest solubility. In 0.01 molar NaF. And if you look at the answer key says that it is the calcium nitrate, but that's because I was not thinking when I made this worksheet. So the answer key is wrong. I actually didn't mean for this to be a math problem at all. I meant for you to look at the concentrations and go, oh, bigger concentration, less soluble. And instead, what did we get? We got this crazy equation with multiple things. However, when we come to the actual math stuff, having seen this before, I'm hoping it will make it all happier in your brain, okay? We will have a quiz on section 3.2 on Friday, and this is not on the quiz, okay? None of the math stuff is on the quiz on Friday, okay? What I was trying to get at was this special name, which is now hidden amongst all the math. The special name is called the common ion effect. Now we're getting back to qualitative stuff. Do you guys know what it means to have something in common?
Yes.
What does it mean if you have something in common with your neighbor? You have something the same as your neighbor, yes? So if we have a common ion, it means the two compounds have an ion, in common. So if we are interested in AgCl2, now to be honest, the common ion effect is nothing new. It's exactly what we've been doing. We've just given it a name. Okay? And that's because out in the chemistry world, when you add an ion that is in common, it's called the common ion effect, and the common ion effect decreases solubility. So for example, two things we could add to our silver chloride to decrease the solubility. One of them would be NaCl, because the Cl is the common ion. It is in common with AgCl. And if you were to add sodium chloride, what would happen to the solubility of AgCl? The chloride ion concentration would increase. That causes a shift to the left, which means that the solubility decreases. Is that anything new? No, we've just given it a special name. Okay? We're now calling it the common ion effect. Sometimes you'll see those words. Sometimes you'll just have questions like the other ones where we don't have to give it that fancy name. Okay? You could also do it with something else where we have the silver in common, right? We have silver in common, and that would again increase the concentration of silver, which would shift the equilibrium to the left, which would decrease the solubility. So the common ion effect decreases solubility. Alrighty? So you can see here, if we have silver chloride, any one of these compounds that contains a chloride ion will cause the common ion effect. Yes? So all of these compounds will decrease the solubility of silver chloride. Is good? Okay. Does changing an ion concentration have an effect on the solubility of a low solubility compound?
No. Yes. Because it has not already reached its maximum level of solubility. So even if you add a little more high, think the solubility would not matter. Like the eight, if the eight B solubility is less than B, we just can reach the maximum of the
So does changing an ion concentration, so for example, if we increase the concentration of A, would that affect the solubility?
Yes.
Yes, because that would cause an increase, for example, which would cause it to shift. So the answer is yes. Okay? The equilibrium will either shift left or right, making it more or less soluble.
Oh, right.
And now for the tricky part. Does changing the ion concentration have effect on the solubility product constant, the KSP? So it does cause a change in the solubility. Whoops. Does it change the solubility product constant? No, why not? Because it's a constant. And what's the only thing that can change KSP? The only thing that can change the solubility product constant is temperature. Is good? Okay, are we ready to look at two things that don't change solubility?
Yes.
Okay, and then we're done. All right, things that do not change the solubility of a salt. Adding more water, adding more salt. Imagine you have a saturated solution of a salt, and now we add more water. What happens? So we have our beaker, and because it is saturated, we are at equilibrium, yes? And we've got some solid here. And this is a saturated solution. So some is dissolving, some is precipitating. What will happen if we double the volume? Will more salt dissolve?
No.
I want you to think about what you just said. So you have taken a cup of water and you've dumped in some salt and you've stirred it around and now there's some salt left. Now you add another cup of water and you stir it. Will more salt dissolve? Really? You cannot dissolve more salt in 2 liters than you can in 1 liter? Of course you can. Yes, yes. So will more salt dissolve? The answer is yes. However, remember, what is solubility? Solubility is the amount that dissolves.
The given amount.
In the given volume. And what have we done to the amount of salt that will dissolve? We've increased it. Let's say we've multiplied it by 2, because what did we do to the volume? We took the volume and we multiplied by 2. So we've doubled the volume and we've doubled the concentration. So the ratio remains the same. The ratio, which is the solubility, stays the same. So yes, you can dissolve more salt, but it doesn't make it any more soluble, because you'll end up with twice the volume as well as twice the dissolved salt. So adding water does not increase the maximum concentration. What if we add more solid? Will more salt dissolve? And we're going to assume that the solid doesn't actually change the volume of the solution, okay? Will more salt dissolve? No, because the water is already saturated. It is full. Saturated is full. So if you want to use an analogy like with a hotel, right, where the salt checks into the hotel, you have the maximum amount of guests in the hotel over here, right? If you bring more guests to the hotel, and these are the people who are waiting outside, yes? If you bring more people to the hotel is still full. You'll just have a bigger queue of people waiting outside, yes? So this is already saturated. It's already full. Cannot dissolve more. So this is beaker A, this is beaker B. What happens to the rate of dissolving and the rate of recrystallization in beaker B when we add the extra salt? Now, what I want you to do is list to your partner the things that affect the rate of reaction. There are 5 of them. 5 things that affect rate of reaction.
Oh. Okay.
Okay, what's one thing that can affect the rate of reaction? Temperature. Concentration. Surface area.
Pressure.
Catalyst and pressure volume. Which two do we not need to worry about here at all? At all. Pressure volume because we don't have a gas, and catalyst because I have not said we've added a catalyst. So which of the other 3 factors, concentration, temperature, and surface area, is changing here? Surface area has changed. Yes, if you put in more solid, you will have more surface area. Okay? And if we have increased the surface area, what has happened to the rate of dissolving? Dissolving has increased. What has happened to the rate of recrystallization? Think about that one. Where does the recrystallization occur? It occurs at the surface. Yes?
Yeah.
So if we have increased the surface area, what happens to the rate of recrystallization? It increases, and they increase by the same amount, by different amounts, by the same amount. And that is why the solubility does not change, because even though you've got more stuff dissolving, you also have more stuff recrystallizing. Yes? And your homework is going to be pages 41, 42, 43. Pages 41 to 43, quiz Friday on 3.2. There will be no math other than maybe doubling an ion concentration. Okay? So it's all about changing solubility with KSP. And hopefully your quizzes will be back tomorrow. I'm working on them.